In this problem, we're going to practice applying the method of departure functions in order to calculate thermodynamic properties in our system. And so what we're going to look at is a fairly straightforward system. What we have is methane entering a turbine where the inlet stream is at a temperature of 600 Kelvin and the pressure is at 10 bar. And the outlet stream, we're even told both the pressure and the temperature. It's 400 K and 2 bar. All right? And what this problem wants us to calculate is what is the work that is produced for each mole of gas. Okay? And the problem asks us to, for our equation of state, it asks us to use, or it gives us the van der Waals constants for this methane. So implicitly it's telling us to use the van der Waals gas equation of state. It also tells us that we can just look up the ideal gas heat capacity for methane in the back of the textbook as well. Okay? So what I want you to do at this point is, based on this text in the problem statement, I want you to sketch out a flow diagram for the system. Okay, based on this problem statement, we could sketch out a turbine flow diagram that looks like this, where our basis is 1 mole per second, and our inlet stream, we're given pressure and temperature, and our outlet stream, we're also given pressure and temperature as well. And I went ahead and I even did the material balance to show that the molar flow rate going in is the same as the molar flow rate going out. And what we want to figure out for this turbine is what is the amount of work that we're able to extract from it. Okay? All right, and so we have one unknown. And so we need one equation, kind of, to solve for this one unknown. For our analysis, we're going to make some assumptions. We're going to assume that this turbine is operating at steady state, and that we don't care about changes in kinetic or potential energy. That this turbine is operating adiabatically, and also, as suggested by the problem, we're going to assume that this gas behaves as a van der Waals gas. Okay? All right, with those assumptions in hand, if we did the material balance, it'd be very straightforward. We get that N1 is equal to N2, which I'll just call N dot, 1 mole per second. And from the energy balance, it's also, relatively straightforward. We have an open system, so we'll use the open system form of the energy balance. We're at steady state, left-hand side goes away, adiabatic, right? These molar flow rates, we could rewrite as just N dot. And so, if we rewrite our equation, what we get is that the shaft work divided by the molar flow rate is just equal to H2 minus H1. Right? So the energy balance itself is very simple to derive. Now, to figure out the shaft work, what we need to do is we need to figure out what is the difference between H2 and H1. Alright, and so in this problem, what we're going to do is, rather than just use a direct application of the calculus of thermodynamics, is we're going to go with the departure function approach. And by doing this, you'll kind of see how it kind of acts like a shortcut for doing these analyses. So let's apply departure function approach. Okay? Alright, so we have H2 minus H1. According to the departure function approach, it splits up, and so these are, the difference in enthalpies of the real, actual methane gas, right? So we haven't made any assumptions yet here. Alright, in the departure function approach, the way we calculate this difference between enthalpies is we split it up into an ideal gas contribution, and then we have another contribution that accounts for all the non-idealities in our system. Okay? And so if we want to calculate, so just to term on the left-hand side is the total delta H. The first term on the right-hand side you could think of as an ideal gas, delta H. And then the second term on the right-hand side, non-ideal, delta H. And so that's how the departure function approach splits these things up. All right, and so if we want to calculate the total delta H of the methane gas as it passes through the turbine, what we need to solve for first, or what we can solve for first, is the ideal gas contribution. Right? All right, and so for an ideal gas, the enthalpies are only going to be a function of temperature. Okay? All right, and so we could write the ideal gas delta H like this. All right, where this is that ideal gas heat capacity, constant pressure heat capacity. Okay. All right. Now for methane, a lot of times we assume that the constant pressure heat capacity was constant, but in reality, when we're dealing with gases and things, even if we're dealing with an ideal gas, the heat capacity itself is going to be a complex function at temperature, right? And so to figure out what the heat capacity function of methane is, it's similar to what you did back in MEB2. You could actually just look up in the back of the textbook the heat capacity function, right? Or in fact, before I even show you this, the heat capacity function typically is modeled as a polynomial where you have your coefficients A, B, C, and D, and typically it's a ternary or a polynomial of order 3, okay, with respect to temperature. This isn't a derivative, this is just the coefficient D times temperature cubed. All right, and so in order to figure out these coefficients, a lot of times these will be tabulated for various chemicals. And from our textbook, as I already just showed you, our textbook actually lists the coefficients for quite a few chemicals. All right. So, for example, in the table here, we see that methane is the very first chemical listed, and we have the A, B, C, and D parameters listed here. So one note of caution, this table is set up similar to the table used in your MEB2 book, where the B, C, and the D parameters, the values that you see here are actually the parameter multiplied by like 100 or 100,000 or 1 billion. And that's just so they could get these values, all the values to fit on the same table. Okay? All right, and so when our A parameter is just 19.875, but our B parameter is not 5.021. It's actually 5.021 divided by 10 to the 2. Okay, so just make sure to punch in the correct number when you're using these ideal gas coefficients. In any case, from the textbook, we could write down what each of our parameters are. And make sure you pay attention to the units as well. So typically the difference between each of the coefficients is the superscript on the temperature unit. And to emphasize, you could see here how when I write these down, I'm accounting for making sure that the actual values of the coefficients are being written. So I'm dividing them by 100 or 100,000 or 1 billion. Okay. All right, so these are the A, B, C, and D parameters in our textbook. And so when we go out and integrate the heat capacity function, what we get is this. Same thing that you saw in MEB2. Okay. All right, and so if we plug in for T2, T1, and all of our coefficients, what you get is that H2 minus H1 is equal to negative 9,289 joules per mole. Okay? All right, so that is, the first part of our total delta H, right? And the way we solved for it was the same way that we've solved for it since MEB2.